Hey guys, welcome to Calculus Day 1. Personally, I don't say this a lot, but calculus is, for me, one of the best math classes you can take at the level of understanding that you have. Um, it is unique among many math classes because if you understood perfectly everything that came before it, calculus is a breeze. It'll be the easiest math class you ever took. Because most of calculus is an expansion upon previous ideas and taking those previous ideas to a new level. We will talk in this class over the next few weeks about how to do things like factoring, but doing them in a way that is wholly unique, or using the results of factoring in a way that you never would have thought would have been important or necessary or even useful, and then talking about how those things become useful and become important and can solve many, many advanced problems of today. Calculus, at its purest form, is the study of change, how a function changes, how a function acts, and how to predict those changes by looking at either the equation, a table of values, or a graph, and then using that information to better understand both the nuts and bolts of an equation, like the x's or the y's, the z's, but also their realistic applications to bigger and larger real-world problems. Because for the first true time, calculus is one of the first classes where, if done correctly, it is more real-world than anything else. And that is because calculus was created to solve realistic problems, problems that needed to be solved. Now, a little preview. I do like to talk history because it is important to understand history in order to see why sometimes math is taught the way it was. Mathematics started with arithmetic. It started way, way back. I mean, you can talk Egyptian, Mesopotamian, Chinese cultures studied math very well, but I'll say at the basic levels. Things like manipulating numbers, arithmetic, and geometry were very common. It was oftentimes used to do things like predict floods so that you could better grow crops. It was used in the Chinese culture to predict things like eclipses, which were believed to be signs of goodwill or badwill when going to war or when harvesting. And so mathematics at its purest form was used as a realistic standard. And starting in the 14, 15, and 1600s, mathematics began to expand dramatically as people understood that you could, in fact, look at math and equations and values in a totally new way. And this new way was developed by two mathematicians. Sir Isaac Newton, who was the British mathematician who discovered it and claimed it first, but a German mathematician by the name of Leibniz discovered it very close in time and completely separately. And they each have their own methods by which they do calculus. And when we talk about calculus, some parts of calculus stick to the Newtonian method, whereas other parts stick to the Leibniz method. And there'll be times when we talk about both. Before we get into the real big parts of calculus, I want to spend the first 2 weeks discussing kind of the preambles to calculus, to get you ready for calculus. It is my goal to not just get you ready for calculus, but to give you some hints, some lead-ins, the first few months of calculus. In fact, we'll actually cover, at a basic level, everything for the entire first semester, or first half of calculus. And in the second half, you'll learn about on your own with your teacher in the future. The reason for this being is, well, most of what takes so long about calculus, the reason why it takes a year for some classes or a semester for others, is because it's a lot of diving in deeper and deeper and deeper and seeing the realistic applications. And so we want to get to that. Before we can do so, we need to talk about kind of the nuts and bolts of it. And so the first week or so is going to be in that vein. So let's get started. I have here a piece of paper. I'll use this to take all my notes on, and so you can kind of see our thought process as we go through. When it comes to calculus, there are three primary ways we view calculus. We've already discussed these. There's something referred to as the analytical approach. There's referred to as the numerical approach. And there's the graphing approach. In a good calculus class, we will discuss all three. And we will in this class, because we're a good calculus class. Now, the analytical approach involves looking at the equation. It involves looking at it and seeing what can I do, what calculus, what math can I do with it. So it's about looking at an equation like something from algebra, y equals 3x minus 7. When you look at this equation and try to do things with it, this is referred to as the analytical approach. It's the direct method. The numerical approach is done by looking at values, or as they're often referred to as points. And this is a completely separate method, because it focuses not upon looking at the big picture, but on looking at specific times. And so the analytical approach is the very mathematical approach. This is mathematics preferred, okay? The numerical approach might only give you a table and say things like, 0, 7, 1, 4, 2, 1, 3, 4, and then 4, 7. This is more real because it's not common in the real world to get a nice function when you look at something. You typically get just instants in time. I check the weather at midnight, 1 a.m., 2 a.m., 3 a.m., 4 a.m., and this is what I get. I check my tire pressure, and this is what I get. I don't test it and get a function, I get values. And so the numerical approach is very, very specific on how it approaches these values and how it gets these values. Now, the graphing method is a combination of these two because it focuses on looking at the graph. And the graph can be found by either using the analytical approach to get an equation or the numerical approach to plot individual points. Now, of these three, the top one is by and far the best one, and where we'll spend the majority of time in calculus. The middle one is typically the more real-world application, and so it's the second most. But the one that tends to be the toughest is the graphing one. For whatever reason, people in mathematics tend to not enjoy graphing, especially at the middle and high school level. Graphing is seen as something scary, something that is difficult, something that is very much not what we want to do. And so you'll find that throughout this class, we will spend a significant amount of time talking about graphing, because if you can understand the graphing part of it, you will be ahead of the curve compared to everybody else, both literally and figuratively. So, today, we're going to spend some time talking about graphing. Now, as part of today, we're going to spend a significant amount of time talking about some terminology. We're going to spend time talking about when we look at a graph, what are the key terms and ways we do graph something. And so, as we're talking about these, many of these will be very low level. There'll be things you did in Algebra 1, Algebra 2, and College Algebra if you took College Algebra yet. But do note, we will expand upon these later, and so making sure we all have the same basic understanding is very important. Let's get started. Okay, first thing. When it comes to graphing, there are two main schools of thoughts. The first one is referred to as point plotting. This is typically how you did it whenever you were in, elementary school. You would take an equation, like, say, this one, y equals x squared minus 2, and you would create a table of x's and y's, and if you did it correctly, you would pick some, x values. You'd then plug those x values in to get y values. So negative 2 squared is 4, minus 2 is 2. Negative 1 squared is 1, minus 2 is negative 1. 0 squared is 0, minus 2 is negative 2. 1 squared is 1, minus 2 is negative 1. 2 squared is 4, minus 2 is 4. So we use this analytical statement to get a numerical statement. And then, based on that information, we would plot a graph. That graph would consist of our points, negative 2, 2, negative 1, or negative 1, 0, negative 2, 1, 2, and we'd get some points. We'd play a fun game of connect the dots to get our lovely equation. Now notice that I'm being very bare bones here. That's because most calculus is less concerned with the more details of algebra. It's expected that you know these already. But this is how most people in Algebra 1 and even into Algebra 2 focus on how to graph. You pick values to get an equation. Now there's an issue with this, if you haven't already noticed. If you pick values, because you're picking them, I picked -2, I picked -1, I picked 0, I picked 1, I picked 2. If you pick those values, the main issue is you need to have representative values. Meaning it's possible the numbers you picked are bad. Meaning when you play this fancy game of connect the dots, it's not actually what the equation looks like. Take a look at this equation. The equation is y equals, and this is a little more complicated, but it has the same basic rules, right? 1/30 x times 39 minus 10x squared plus x to the 4th. Here's the thing. If I immediately jump to this method and say, hey, let's plug in some values. Let's say I happen to pick some numbers. And let's pretend for a moment we actually pick the following numbers. We pick -3, -1, 0, 1, and 3. Here's the thing. If I was to take these and plug them in, if I plug in -3, I will save you some time here and do the math for you. If I plug in -3, I get -3. If I plug in -1, I get -1. If I plug in 0, I get 0. If I plug in 1, I get 1. If I plug in 3, I get 3. And here's the funny part. If I was to sketch this graph with just the information I have been given, look what happens. -3, 3, -1, 1, 0, 0, 1, 1, 3, 3. If I were to sketch this graph, it looks like a line. This is a false representation. Because it turns out the actual function looks a little more like this. It does some very interesting curves. In fact, in a little bit I will bring up a picture of this thing so you can see exactly what it looks like. It has some weird little curves in here. It sort of levels off in between the -1 and the -3. It then comes back up, hits through 0, levels off again between 1 and 3, and then starts shooting back up again. It has this weird little flexiness to it. You can't get that from the numbers we got. And so you can see that by point plotting, there is a significant problem, that the points you choose matter a lot. And so when you're doing point plotting, you have to make sure to always pick values appropriately. What this means is you need to pick enough numbers to get a good picture, but at the same time these values need to be based upon something that represents the function. And so knowing properties of the function can help with this. Because anytime we talk about point plotting, it's possible that the picture you have is not good. This is really common in trig functions. If you have not taken trig yet, I apologize. It kind of sucks to be you. Because if you pick up a trig function and it's something like cosine of pi x, and you attempt to graph this thing, if you pick numbers like -2, -1, 0, 1, and 2, then when you plug those numbers in, you'll find that every single one of them gives you one of two answers. It gives you an answer of 1. Every one of these gives the same answer. And so when you graph it, it looks like all that's happening is you're going like this. And so it looks like a line. But in fact, in this example, what's really happening is it's doing this. And so if you fail to pick good values, you will not possibly be able to get to a good graph. And so you can see that when it comes to plotting points, you have to be very particular about how you plot them. Now to help with this, many modern mathematicians have embraced technology in order to better make sure that we were able to do this very well. And so technology allows us a bunch of advantages. The first advantage is it's very fast. The second advantage is, of course, that it's nowadays fairly cheap. I have a graphing utility on my calculator that was free. I use it quite often, but it kind of depends upon what you're using. And so just give me a moment. I'll pull up my graph. You can see right here, this is my graphing utility. This is a free program I managed to get online. And there are numerous programs online that you can find that actually give you this exact same usability. And if I showcase my two functions, okay, so if I do cosine of pi x, you can see how that function is graphed. I was making this nice squiggle, but depending on the values you choose, you may not see that squiggle. You may only see a straight line. And so that happens. Or equivalently, if I choose the other one, which was 1 over 30 times 1 over 30 x harder on a computer than it is by hand. 1 over 30 x times 39 plus minus 10x squared plus x to the fourth If I've got this function instead, you can quite clearly see how it has this, weird little hoppy hop system. And you wouldn't see that if you picked the wrong values, okay? Because again, if you look at the table, you can see that -3 is 3, -1 is 1, 0 is 0, 1 is 1, 3 is 3. Like, you can see that if you pick the wrong values, you will manage to get a function that does this. Now, people sometimes ask, what functions do I use for my personal computer, my personal phone? I use two. So this is my phone. It's beautiful, I know. Darth Vader, very common and fun. I have two that I use. I use Desmos for if I want to do things for like algebra or even trig. Desmos is very useful, and it's free. However, it does have a little bit of a learning curve, so I recommend taking some time to learn it. And the other one is a fancy one called Wabbit Emu. And I'll write that one down. It's free if you have an Android. If you do not have an Android, it is not free, sad to say. And I've been trying for a long time to see if I could find a better one, but so far it's the best one I have. What Wabbit Emu does is it turns your phone into a calculator, a TI-84 specifically, which is pretty nice. And you can even go in and change what kind of calculator it is, so you can do like other TIs specifically. And there are similar programs out here that will turn these into Casios. Now, for calculus, I would strongly recommend to either have a TI-80 something. I use a TI-84 Plus. That's the one I use. You can use Desmos for a lot of this, which is a free app, and works on your desktop if you have a computer. The last thing I would tell you is that you can even use the Casio. The cheap $15 Casios are actually pretty good for this too. They can't graph, but these two are great for graphing. And this one's good for non-graphing stuff. So if you've got to spend money, just buying the Casio is fine. And then getting Desmos to get the graphing stuff done. So there's that information, just so you have it. Alright, let's continue. When it comes to graph, there are some very specific things about the graph that are considered important in mathematics. And for us specifically, they have two, or in this case, three major categories. The first category, intercepts. I refer to these as points of interest, POIs. So intercepts are major points of interest when it talks about the graph. Because as it turns out later on, these are places where something unique can happen specifically to do with the calculus. There are two intercepts that matter, the x-intercept and the y-intercept. Now, in a graph, let's go ahead and go down here and draw a very simple graph. Let's go like this. These three values are the x-intercepts. They are defined as the places where your graph crosses the x-axis. How do we find these? The easiest way to do is to let y values equal 0 and then solve them. The y-intercepts, on the other hand, are the places where you cross the y-axis. Remember, your x goes left to right, your y goes up and down. Your y-intercepts are found by letting x equal 0. And, of course, solving. Let's look at that simple equation from before. Y equals x squared minus 2. If a question asks you to find the intercepts, it's very simple. All you do is you have to do two problems. The first problem is to find the x-intercepts. You plug a 0 in for y. Second problem is to find the y-intercepts. You plug a 0 in for x and solve. So like on this one, I could move the 2 over, giving me 2 equals x squared. Take a square root of both sides and get x equals the positive or negative square root of 2. Remember, when you take a square root, you should get 2 answers. On this one, I can do the same basic concept. Order of operations would state I do the power first, so 0 squared is 0, minus 2, which is negative 2. And so in my previous graph, I would say that if I wanted to know what the intercepts are, the x-intercepts are at negative square root of 2, 0, and positive square root of 2, 0. The y-intercepts are at 0, negative 2. Notice that how we solve them also matches how we write the solution. In the x-intercepts, the y value is 0. So here's an x-intercept, the y value is 0. Here's an x-intercept, the y value is 0. To find an x-intercept, the y has to be 0. To find the y-intercepts, the x has to be 0. So notice again, in my solution, whatever number I get, the x has to be 0. So my answer is what the y value is, negative 2 in this case. And for any problem, you can use this to determine what kind of x and y intercepts you have. Let's look at another one. Same basic concept. Now, to note, this is an analytical approach because we're using the equation to find these things rather than looking at the picture to find these things. This was the more common method because for a lot of time there wasn't technology that existed to do this. And so being able to do it by hand was a very important skill. Okay, let's write this one. X cubed minus 4x. Okay, let's do this. So, for this problem, we need to determine where the intercepts are. We break it into two parts. Part 1. We let the y value equal 0, and we solve. Part 2. We let the x value equal 0, and solve. Now, if you remember everything from previous classes, these are easy problems, because if you look at the first one, all you do is you'd factor an x out. You get 0 equals x times x squared minus 4. You see that this second part is difference of squares, x minus 2, x plus 2, and then we get to our three solutions. X equals 0, x equals 2, x equals negative 2, meaning my answers are 0, 0, 2, 0, and negative 2, 0. If you remember everything perfectly, then this is really easy to do, because it's just Algebra 1 and Algebra 2 work. If you don't remember perfectly, then this is hard to do, because you have to remember something that you don't remember. Down here, this one's pretty easy. 0 times anything is 0, 0 plus anything is 0, so we end up with the value of 0, and so our y-intercept would of course be 0, 0, But then again, we already knew that because it was right there. So if the question asks you to find the x and y intercepts, or more specifically, it says to just find the intercepts, this is the process. We plug in x equals 0 to find the y's, we plug in y equals 0 to find the x's. The last part of today, the last major part of any graphing problem, is to understand probably something that you haven't thought about in a while, because it tends to be a geometry topic and not an algebra topic, symmetry. When it comes down to it, symmetry is how a function looks. There are three types of symmetry. Type 1, symmetry around the x-axis. Type 2, symmetry on the y-axis. 3, symmetry around the origin. Now each of these has distinct different looks, and it really depends upon how you see them that it matters the most. So let's take a look at each one of these in particular. So around the x-axis means that if you take a graph, so this one I'm going to do my x-axis here in blue. Okay, so what does symmetry in the x-axis look like? Well, here's a good example. This is symmetry on the x-axis. Why is it symmetry on the x-axis? Because you can clearly see that if we were to take this graph, there's a folding nature to it. That if we were to fold along the x-axis, the top and the bottom should match. This is the idea of symmetry. On the y-axis, here in red, we'll showcase symmetry about the y-axis, which is actually in most cases the more common one. A good example of this might be something like an absolute value function. And so this red one isn't, because if we fold it along the y-axis, and we folded these two sides upwards, they should match left to right. Whereas the last one is the origin. Origin is kind of the trickier one, so I'm going to put that on its own graph here. Unlike the other two, which involve folding, the one about the origin doesn't really fit those parameters. Now, visually, symmetry is fairly easy to see, which is why the technology portion is so important. But there's also something called the test for symmetry, which we'll talk about here in a moment. And it's an easy thing you can do algebraically to see if you get the same results. So, these are the three different types. These have to do with how they could look. There is a fourth type. No symmetry. And if you want to see an example of what no symmetry looks like, that thing over there. I can't fold the x-axis and make it match up because there's nothing up here for it to match to. I can't fold the y because there's nothing over here to match to. And the origin you can think of as rotating 180 degrees. And so if I rotated this circle 180 degrees, it ended up over here. And so again, there's no good way to have this. And so in this case, this is referred to as no symmetry. It is possible for a function to have x symmetry, y symmetry, origin symmetry, no symmetry. And it's possible to have a couple of these. But it's possible to have both x and y. It's possible to both have x and origin. It's possible to have both x, y, and origin. But symmetry is the lone dog. It's always by itself. And this leads us to our last piece for today. How do we test for symmetry? Okay. There's three tests. If it passes any of these tests, we say it has that kind of symmetry. If it fails all three, we would say it doesn't have any symmetry. So, let's look at the first one. Replace y with negative y. all three of these, we're going to use the same phrase. Does the equation stay the same? So if I substitute y and negative y, so everywhere there used to be a y, I replace with negative y, and the equation somehow doesn't change, it stays the same. If that answer is yes, we call this x-axis symmetry. If the answer is no, then not x-axis symmetry. If you were to replace x with negative x, and I asked that exact same question, and it turned out that it did stay the same, we'd say there's y-axis symmetry. And if not, we say that's symmetry. Now, for the origin, you do both. You take x and replace it with negative x, y and replace it with negative y, and does it stay the same? If the answer is yes, we say origin. If the answer is no, we say there's not. These are the three tests. Now note, since the third one has you testing both, if the first one fails, then the third one's going to fail. So you can save yourself some headache there. If the second one fails, then the third one's going to fail. Save yourself some headache. And so you can see how these pieces kind of all fit together. Let's look at an example before we finish. Let's look at the equation. Yeah, I like that one. Y equals 2x cubed minus x squared. Let's test this thing out and see what happens. So, let's start by doing our first test. Our first test says take y and replace with negative y. Okay, so when I do that, watch how the equation changes. My y becomes negative y. Now, in order to do this, I need to make sure y is by itself and fully simplified. So I'm going to take a step where I'm going to divide both sides by negative 1 in order to get y by itself. Because my original equation has y by itself. I want to see if this is the same as that one. And it turns out if I do that, I will get negative 2x cubed plus x squared. You can clearly see these two are different, so there is not x symmetry. So again, my goal is I need to compare the new equation with the old equation. This is my new equation, simplified. This is my old equation. Do they match? No. Let's do it again, but now the other type. X to negative x. Well, what's it look like? Y is still y. 2 negative x cubed minus x squared. And then we simplify. Y is just y. Negative x cubed would be negative x cubed. Negative x squared would be just x squared. But you'll notice again, these two equations, my plugged-in equation and my new equation, don't match the original. So this is not y-axis. Since both of these fail, we could check to see, do we actually end up with the same equation for the third one? No. There's not origin. And so we'd say this equation has no symmetry. At least according to these three specific examples. And if I pull up my graphing calculator, you can always test these just by plugging it in. Click on the graph, I can test out 2x, oops, 2x, no, dang it, I gotta do my hand, 2x to the third minus x squared. There's the graph. You can see how it's just a little bit off. I'm going to zoom in a little bit. Use the zoom command. can see how this side's just a little bit farther to the right than that side. It's just a little bit off. But that little bit matters, because it means there's no symmetry. And so it can't be folded left or right, as you can clearly see. It doesn't match left or right. It can't be folded up or down. It's not rotated because it's just a little off here. And so this one has no symmetry. Now, for tonight, you'll have a couple of problems tonight that ask you about how to determine when something is symmetrical and find their intercepts. Now, for these problems, I've asked you to do 3 things. I've asked you to sketch the graph, and you can use a gravity calculator to help with that. But you can use the point method as well. I've asked you to find any intercepts, and then test for symmetry. Now, if you remember everything from Algebra 1, Algebra 2, and College Algebra, this should be pretty straightforward. If you don't, this is a good time to play catch-up. This is why we're doing this kind of stuff over the summer. It's not to learn a brand new skill. It's to get better before we have to learn it for real. And so those are our 3 things. We're having sketching a graph. We have finding intercepts and testing for symmetry. And that'll be it for today. I wish you guys a good Tuesday. Hope you guys enjoy the rest of your day. I'll see you guys tomorrow.